Welcome, everyone. Today, we are going to explore a truly fascinating topic in medical entomology, the insect head and eyes. Imagine stepping into the cockpit of a highly advanced fighter jet, packed with sensitive sensors and complex controls. For an insect, its head serves exactly this purpose. It is the ultimate survival toolkit, and understanding it is the absolute foundation of vector control. Let us dive in. Now that we have introduced our topic, let us look closely at the insect head itself. Why does this structure matter so much? Because without this heavily armored capsule, a vector like a mosquito could never locate a host or pierce human skin. The head is a hardened, heavily sclerotized capsule formed by the evolutionary fusion of several embryonic segments over millions of years. This fusion creates a rigid, protective box. Not only does it shield the delicate brain, but it also provides incredibly strong attachment points for the powerful muscles that operate the mouthparts. It is a masterpiece of biological engineering. Building on that anatomy, we must understand that not all insect heads are positioned the same way. The head is typically oriented in one of three ways, depending on how the insect feeds. We have hypognathes, where mouthparts point down, like in a grasshopper. Then there is prognathes, pointing forward, seen in sandflies. Finally, opisthognathes, pointing backward, like a bedbug. This matters immensely for disease transmission. For example, the forward-pointing mouthparts of a sandfly allow it to slice into skin and pool blood, transmitting leishmaniasis. If we do not understand these mechanical structures, we cannot design effective physical barriers. This mechanical structure we just discussed leads us to an important mathematical relationship. To understand how tiny insects can bite through tough skin, we look at the mechanical advantage of their jaw muscles. The head acts as a rigid lever system. In this formula, M represents the mechanical advantage, a unitless number showing force multiplication. F out is the actual biting force, while F in is the input force from the insect's muscles. L in is the distance from the muscle to the jaw pivot, and L out is the distance from the pivot to the biting tip. When the in lever length increases relative to the out lever, the mechanical advantage increases, meaning the insect bites much harder with the exact same muscle effort. Before we look at the final biting force, let us first calculate the mechanical advantage using our new formula. Imagine a blood-sucking insect with an in lever of 2 millimeters and an out lever of 0.5 millimeters. We need to find how much the head amplifies force. We use the ratio of the lever arms, dividing the in lever by the out lever. Substituting our values, we divide 2 by 0.5. Notice that the millimeter units cancel out perfectly, leaving a pure ratio. The result is 4. This means the insect's head structure multiplies its internal muscle force by a factor of 4, setting the stage for a powerful bite. Now that we have found the mechanical advantage of 4, let us apply it to find the actual biting force. We are given that the insect's jaw muscle generates an input force of 0.05 newtons. We want to find the total output force exerted at the tip of the mandible. We use our force relationship, multiplying the mechanical advantage by the input force. We multiply 4 by 0.05 newtons. The result is 0.20 newtons. Physically, this means the insect bites 4 times harder than its muscles alone could achieve. Without this mechanical advantage provided by the rigid head capsule, the insect would simply bounce off our skin. Now that we understand the feeding mechanics, let us shift our focus to how these vectors locate their hosts. Have you ever seen a massive wall of televisions, each showing a slightly different part of the same video? That is very similar to how an insect sees the world. Instead of one single lens, insects have compound eyes made of thousands of tiny individual lenses. Each lens captures just a small fraction of the scene, and the insect's brain stitches these fragments together into a complete mosaic-like image. Because the eye wraps around the sides of the head, it provides an incredibly wide field of view, allowing a mosquito to see in almost all directions at once. This mosaic vision we just described is made possible by highly specialized anatomical structures. The primary visual organs are made up of repeating functional units called ommatidia. Each ommatidium is a complete visual receptor, consisting of a corneal lens on the outside, a crystalline cone for focusing light, and light-sensitive retinula cells that send signals to the brain. In addition to these compound eyes, many insects also possess simple eyes, called ocelli, usually located on the top of the head. Ocelli do not form complex images. Instead, they are highly sensitive to rapid changes in light intensity. This helps the insect maintain stability during flight and detect the sudden shadows of approaching predators or defensive swats. Understanding the structure of the eye naturally leads us to question how clearly the insect can actually see. The clarity, or resolution, depends heavily on the angle between adjacent ommatidia, known as the interommatidial angle. We can approximate this angle using basic geometry. In this formula, delta phi represents the interommatidial angle in radians. The variable d stands for the diameter of a single ommatidial lens, or facet. The variable r represents the local radius of curvature of the eye. Conceptually, when the facet diameter decreases, or the radius of the eye increases, the angle becomes smaller. A smaller angle means the ommatidia are packed more tightly together, which significantly increases the visual resolution and allows the insect to see sharper images. Now that we have our resolution formula, let us apply it to a disease-carrying mosquito looking for a host. We are given a specific region of the eye with a radius of curvature of 400 micrometers and a facet diameter of 20 micrometers. We want to find the interommatidial angle. We use our formula, dividing the facet diameter by the radius. Substituting the values, we divide 20 by 400. Both measurements are in micrometers, so the units cancel out perfectly. This simple division gives us an angle of 0.05 radians. This value defines the fundamental geometry of the insect sight. While we have successfully calculated the angle as 0.05 radians, radians can be hard to visualize in everyday life. Let us convert this measurement into degrees to better understand the mosquito's vision. We take our radian value and multiply it by the standard conversion factor of approximately 57.3 degrees per radian. Multiplying 0.05 by 57.3 gives us 2.865 degrees. Physically, this tells us the angular separation between two adjacent pixels in the mosquito's vision. While this is quite blurry compared to human vision, it is perfectly optimized for the vector to efficiently detect large, moving shapes, like a human host. Having calculated the visual resolution, let us now visualize exactly what these mathematical variables represent in the insect's anatomy. On screen is a cross-section of the compound eye. Notice the curved outer surface. The distance from the center point to this surface is the radius of curvature, labeled r. Along the surface, you can see individual lenses. The width of one lens is the diameter, labeled d. The angle formed between two adjacent lenses is our interommatidial angle, delta phi. On the right, a single ommatidium is enlarged. You can clearly see the corneal lens at the top, the crystalline cone beneath it for focusing light, and the long retinula cells that transmit the visual signal to the brain. This geometry is what dictates the insect's entire visual experience. To wrap up our lecture, let us review the most critical points we have covered today. First, the insect head is not just a protective shell. It is a highly specialized, rigid lever system that mechanically amplifies muscle force, allowing tiny vectors to pierce tough skin. Second, the specific orientation of the mouthparts directly dictates how an insect feeds and transmits diseases. Finally, the compound eyes equip these vectors with unparalleled motion detection and a massive field of view, with their visual resolution mathematically defined by the interommatidial angle. You have now covered the fundamental physical and optical mechanics of the insect command center, which is the crucial first step in developing better vector control strategies. Great job!